This video introduces the idea of organic chemistry shorthand, and it shows how to interconvert between condensed formulas, line structures, and Lewis structures. Here's an example of a very important biochemical molecule, ATP, also known as adenosine triphosphate. This is a line or skeletal structure view of the molecule and is also known as organic chemistry shorthand. Some elements look very much like a Lewis structure. Here's an oxygen with a minus formal charge. Here's an oxygen with a double bond and no formal charge. The lone pairs are missing on both those oxygens, but you see the oxygen and you see the number of bonds that it has. Here's phosphorus with 5 bonds. Notably missing from this structure are any C's for carbon atoms, and there's only a few H's in the structure. Another interesting element of the structure is these deeper lines. These are meant to give some kind of three-dimensional representation. So this is meant to be coming out towards you, coming out in front of the page, and then going back into the plane of the page. In the next slide, we'll see how to interpret where the carbon atoms are, because there are many carbon atoms in ATP. Here's a much simpler compound, normal butane. This has 4 carbons. Each carbon has its characteristic 4 bonds, and the hydrogens, of course, have 1 bond. So you see that 1, 2, 3, 4 carbons and 10 hydrogens. The molecular formula, which is a very condensed notation, useful mainly for calculating molar masses, is C4H10. It doesn't tell you any structural information, though. A condensed formula that gives you a little more structural information is shown here. This first carbon has 3 hydrogens attached, and then that is attached to a carbon with 2 hydrogens. So that's what's shown, CH3 to CH2 to CH2 to CH3. Or even more condensed, CH3 is attached to 2 of these CH2 units, and then finally to a CH3. The last notation, line notation, looks very bare. Turns out to be incredibly useful, especially when you're drawing with a pencil. Each endpoint and each vertex or place where lines join is a carbon atom, and we'll look at more details of that in the next slide. You'll need to be able to convert between all 4 types of notation, although again, the molecular formula will be the least useful for giving us structural information this semester. Here's those rules. Each vertex, each joining place, and each endpoint, these are the endpoints and these are the vertices, is a carbon atom. And each carbon has to be bonded to enough hydrogen atoms to give that carbon atom 4 bonds. So here's our Lewis structure. C is bonded to 3 H's and 1 carbon atom. This is just another view of the Lewis structure. I wanted to show you that it doesn't matter how you write it on the page, as long as the first carbon has 3 hydrogens and then it's attached to another carbon with 2 hydrogens, and then another carbon with 2 hydrogens, and finally a carbon with 3 hydrogens. It's identical to the structure that's shown with 90-degree angles to the left here. And both of those are identical with the structure here. The first carbon is only bonded to 1 other carbon, and that's what's shown on the diagram. The reader is left to infer that since that carbon needs 4 bonds and only 1 bond is shown to another carbon, there must be 3 hydrogen atoms completing its valence. Likewise here for the second one, there are 2 bonds to carbon atoms, so since carbon needs 4 bonds, there must be 2 more bonds to hydrogen that aren't shown in the picture. Once you get used to it, it's a very nice notation. Here's a more complex molecule with a double bond between carbons. I'm going to pause, or I ask you to pause the video and try to draw the line structure for this molecule, and then I'll show you the answer. Okay, carbon on the end has 3 hydrogens and is bonded to 1 other carbon. So we're going to make a single line from that carbon on the end to the next carbon. That means that the reader will know that the first carbon has 3 hydrogens. The next carbon is bonded 1 single bond out to the end carbon and then a double bond to the next carbon in the line. And we do the zigzag just so it's easier to see the structure. There will be a few exceptions to that when we have triple bonds, and we'll show you those later. So the second carbon has 1, 2, 3 bonds showing, it must have 1 hydrogen. Likewise with the third carbon, 3 bonds showing, so it must have 1 hydrogen, and there it is. The next carbon has only 2 bonds showing in the structure, so it must have 2 hydrogen atoms, as you can see here in the Lewis structure. And finally, the last one looks just like the first one. Here's one more structure. This one has a branch. There are 1, 2, 3, 4, 5 carbon atoms. We can see that over here. 1, 2, 3, 4, 5 carbon atoms. 1, 2, 3, 4 of them are in a line. 1, 2, 3, 4. And the second carbon atom has an attachment to one carbon, another carbon, and a third carbon coming up here. Doesn't matter that this bond is shown with a longer line than the others. Again, we're not implying structural information with Lewis structures. We're not implying shape information with Lewis structures. We're just showing the reader how the connections are made between atoms in the molecule. Here's another example that you can use to test yourself. This is from the Wikipedia reading about skeletal formulas. And this is the antidepressant drug escitalopram. Has a lot of unique elements in it. And I'd like to call your attention to something neat. When you subtract out visually the carbon atoms, because they don't show up as C's, they're just lines, as you get better and better at reading these structures, you'll see that you focus your attention on the atoms that aren't carbons and hydrogens. And those are called heteroatoms, and they tend to be the place where a lot of chemistry takes place. They often have lone pairs. In fact, all 4 of the heteroatoms in this structure do have lone pairs. And again, they are places where interesting chemistry takes place. One more little hint as you test yourself. The wedge line that you see here just implies that there's a single bond coming out towards you spatially. So this is an attempt to give you some sense of spatial extent of this molecule. And the dashed line likewise means a single bond that's moving back away from the plane of the paper. Okay, please pause the video and write out the whole Lewis structure to the best of your ability for this molecule. And do include the lone pairs on all the heteroatoms. I hope you enjoyed that challenge, and here are the answers. We'll just go through a couple of the highlights quickly. First, you see 2 6-membered rings, 1, 2, 3, 4, 5, 6. So here are the 6 carbons, 1, 2, 3, 4, 5, 6. If you start to count, that first carbon with the fluorine on it has showing 1, 2, 3, 4 bonds already, so it doesn't need any hydrogens. The fluorine, of course, needs its full complement of 3 lone pairs. The next carbon has only 3 bonds showing, so that's how we knew it had to have a hydrogen. And likewise with the other, with all 4 of these carbons here. The carbon going down this way has 1, 2, 3, and then the 4th bond to carbons, so it doesn't need any hydrogens. This next carbon likewise has 1, 2, 3, 4 bonds to other elements, so it doesn't need any hydrogens. Something that's sometimes confusing or people worry about, what do you do when there's a bond but then there's an endpoint and it goes to an O? When the bond ends at a heteroatom, there's no carbon right there. That's just straight to the O. So there's the carbon that's at that 4-point juncture, and then there's the oxygen that it attaches to. There's no additional carbon there. So this is a little 5-membered ring, 1, 2, 3, 4, 5, and here are those 5 members, 1, 2, 3, 4, 5. Over here, I'm going to skip these carbons because I think you can do those. Here's a nitrogen. It has 3 bonds showing, and we know that nitrogen's pattern is 3 bonds and a lone pair, so that's how I knew to put 1 lone pair on there. These are also can be a little tricky until you get used to them. When a bond just kind of dangles out in space like that to an endpoint, that you know is a carbon, and because there's only 1 bond to that carbon in the line structure, it must have 3 hydrogens on it. And finally, over here on this side, I promised you a triple bond. Here's a carbon with a double bond, a single bond, and another single bond to it. And this, even though there's not a bend there, is a joint. That's another carbon atom. And that carbon atom has 1 bond off this way and 3 bonds to the nitrogen. So there we show that carbon with a single bond that way and a triple bond this way. This nitrogen gets its 3 bonds, so we needed to put a lone pair on it. And that concludes the introduction to use of Lewis structures or drawing Lewis structures given line structures. You should also practice going the opposite direction. And there are a number of practice exercises in Blackboard for you.